welcome back to lecture 4, which will be about applying what we learned last time about CFD and deriving some bounds on their spectra. But before doing that, let's recall the points of the previous lecture, the important points of the previous lecture, which we're going to need today. So really, the main point of the previous lecture was to kind of motivate, from a physical point of view, a definition of a mathematical object, which we can call a unitary one-dimensional CFD. So here is a reminder of the definition. The key points is that there is some SL2R algebra acting, generated by P, D, and K. This is a Lie algebra with these combination relations. So SL2R, P has a charge 1 under D, K has a charge -1 under D, and K and B commute D. Then we talked about the space of observables, which physically speaking are all the observables which can be localized to a unit ball in general dimension, or in the case of one dimension to the unit interval, so -1 and 1. And by assuming reflection positivity, which is the same thing as unitarity, we can decompose this Hilbert space into unitary irreducible representations of this algebra, where unitarity is equivalent to these hermitativity conditions. So when P, K, and D act on this Hilbert space, they satisfy these hermitativity conditions. And we can decompose this Hilbert space into unitary representations, which are labeled by two quantities, delta and J. Delta is a scaling dimension, which is a positive real number in a reflection positive case. And J is just a Z2 charge, which comes from parity. But the J will not really play such an important role. Now, these representations are infinite dimensional, and they take the following form. They have a lowest wave vector, which is a confound primary. I'm writing C here to mean that this is a one-dimensional complex vector space, which contains all the complex multiples of O. Then there's a first descendant, second descendant, and so on. So each of these are one-dimensional complex vector spaces, and together they form this infinite dimensional representation. Is this notation clear? What I mean by C? Good. So far we have the data delta consisting of delta and J. This is generally an infinite sum, also infinite discrete sum. And then we're going to supplement it by additional data, which is the 3-point functions of OI, OJ, OK. They are the CI, JK. Now, it's possible to choose a basis here such that C, I, J, K are real. Also a crucial point. And given this data, associativity of the operator product implies an infinite set of constraints in this data. And these constraints are called conformal bootstrap equations. They take the following form. So the important aspect is the presence of these conformal blocks. Conformal blocks are special functions of a single complex variable z in this case, and they depend on the parameters delta and the 4 sort of external dimensions, delta 1 up to delta 4, and they take the following form of the hypergeometric function. So these equations are bilinear in the c's and highly nonlinear in the deltas. So the g is a complicated nonlinear function of deltas, but the structure of the equation is bilinear in the c's. As you can see, they always appear here. Okay, so this defines some kind of mathematical structure which mathematicians are only beginning to appreciate now, but physicists have appreciated for a while. And in particular, any unitary CFD in any dimension provides a solution of these equations by putting all of the operators on a line. And they're also inherently one-dimensional. All right. Okay, welcome back. Well, let's do an exercise. Regionalized free boson. So I was mentioning that there are various solutions of this equation. The solutions have not been classified. It would be like classifying all CFDs in all dimensions. But there are some inherently one-dimensional simple solutions of this large set of equations. Yeah, I should say these are equations which are valid for IJKL arbitrary, so from 0 to, maybe I should say from 1 to infinity. Also for all z in the unit interval. So this is the region of real z where both sides are supposed to converge. With some highly infinite set of equations for a highly infinite set of variables. And one particular solution is the generalized free field, generalized free boson, which is defined by saying that, well, it's a Gaussian theory, meaning that all of the endpoint functions are computed by sums over big contractions, pairwise big contractions, and a single big contraction. It's a two-point function which takes the following form. There's a single parameter which is 2 delta phi. So it's a one-parameter family of solutions of all of these constraints. Parameterized by the delta phi. The primaries, as we were discussing at the end of last lecture, are identity, and in various words built out of derivatives of phi. So phi is a particular primary, then all of the derivatives of phi are descendants, so they live in a single irreducible representation. And then the primary is built out of two phi's. They take the following form with alpha j. So they are basically there's two phi's, and they have a total of n. So there's a discrete label n. There's a total of n derivatives acting on the two phi's, j on the first one and minus j on the second one. But this object is primary only if we choose these alpha j's correctly. I suggested to you to do the exercise to find these alpha j's by imposing this as a primary so that k annihilates it. If you did this exercise, you would find this. But maybe let's actually do this exercise together. So, did anybody try doing this on their own? Last lecture. We all have so much free time, right? Let's make up the audience and the computer. So let's do this exercise I was mentioning. We are just going to simply build this operator, phi, the so-called double trace operator with n derivatives, and we are going to impose that it's a primary. And to do that, we need the following fact. The fact is that if we act with k on the nth descendant of phi, well, this has to be some multiple of the n minus 1 descendant. Because the total conformal weight of this is the dimension of phi plus n minus 1, because k decreases the weight by 1. And okay, this is something you can do very quickly. You find that it's n, so the multiple is n times 2 delta phi plus n minus 1 times the n minus first descendant phi. Okay, so this, you find some commutation involving d, and the descendants contributed n minus 1 here. So now when we well, acting with k on the double trace operator is going to produce a recurrence relation for a alpha j, of which this is going to be a solution. So let's do that. So I'm just going to repeat it here. Is this big enough? Yep. If it's not big enough, complain. This is open up. Perhaps bigger. 300. Doesn't get any bigger than that, apparently. That's the limit. Okay, so sum from 0 to n alpha j, and we have for the j descendant on phi and minus j powers of the e on that. Now when we act, okay, so this is what we call phi n.
There's n goes to n minus j.
Yes, if there's it's a little bit redundant, so there's some symmetry indeed. So we should, without loss of generality, we can assume that alpha j is equal to alpha n minus j. And what we want to impose is that k, and it acts on this guy, is equal to 0. So let's do that. Well, let's just act on the sum. So, yeah, okay. Yeah, being very careful about. Wait, so just imagine there's a normal already here. So when we act with k here, then for the first time we are going to decrease this by 1, and we are going to get that factor, which is 2 delta phi plus j minus 1. Yes, that's from the first term, and then from the second term, we are going to get instead we are going to decrease we are applying the product rule. So it acts on the second one, decreases the power by 1, and then we get n minus j instead of j, and 2 delta phi plus n minus j. Okay, let's make it a bit bigger, and this needs to be equal to 0. Okay, so now we need to put together the same operators. So to do that, we should shift j by 1 over here. So let's do that. You see the j equals 0 term doesn't really contribute, and now we can instead relabel j to be j minus 1. So we're just going to shift everything here by 1. Okay, if we shift it here by 1, we get rid of that. If we get rid of that, and here we get this 1. Okay, so now you can see these two objects are the same. So we can safely set the total coefficient to 0. So the recurrence relation is this one, which allows us to solve, the plus is equal to 0, right? So the equation looks like that. So we can solve for alpha j plus 1 in terms of alpha j as such. Actually, okay, now we just need to check that this formula gives you the right answer. But you can sort of see the structure. If we maybe just shift this if we shift all the j's by minus 1. Okay, so now you can. Let's solve for alpha j in terms of alpha 0. So every time we apply this recurrence, we get 1 minus sign. So that's why there's a minus 1 to the j. Then from the factor downstairs, we get a 1 over j factorial. Then from this factor here, we get the Pogammer of 2 delta phi. And well, from here, we get something that's n factorial over n minus j factorial. You can, I'm doing this fast because I already know the answer, but you can probably quickly see that it's correct. And then from the factor over here, you get Pogammer 2n. Over there. So yeah, the claim is up to an overall constant. Up to an overall constant, it looks like that. Actually, I didn't write the n factorial, but it's just an overall constant, so we can also get rid of that. We just care about the j dependence for now. Of course, the operator is not normalized yet, but let's just check that we didn't make any mistake. So alpha j plus 1 times this plus alpha j times that should be 0. We have a formula for alpha j. Now this formula is only symmetric under j goes. So remember, we had the symmetry where j goes to n minus j. So this formula is actually symmetric under the operation for even n, and it's antisymmetric for odd n. So this is why this operator only exists in the bosonic case for even n. But if I were a fermion, then all of the same arguments would go through. But now this operator would only exist for odd n, and this will play an important role. That's true. Now, as I said, this operator is not yet normalized. It's phi n. So let's actually compute its normalization. To do that, we just need to compute a two-point function. We want to compute a two-point function of phi at x1, phi at x2. In fact, since these are primaries, they should be orthogonal to each other, and we'll be able to check that. So what we should find is that there is going to be a Kronecker delta in the n space, n1 and 2. There is going to be the conformal two-point function for a primary of dimension 2 delta phi plus n. And finally, there should be some overall constant, let's call it little a of n1, which is the total normalization. And for what I'm going to do later, we'll have to compute this a of n1. So let's check all of these claims now. So what we want to do is we want to compute the table of these two-point functions. Let's say up to some n max. So this modulo, I'm just going to set n max to something small for now. So n. Now p is just a derivative. So what we need to we are summing. Sorry, I should be more careful here. Let's define alpha to be also a function of n, not just j, but also of n. So here we have a double sum over j1 and j2, right? Because we are inserting two of these operators phi. So sorry, we should be summing. This is just a table for now. Let's do it later. And what we should be doing is that we should be summing over j1, which goes from 0 to n1, and over j2, which goes from 0 to n2. And the coefficient of the sum are just the product of two alphas, one for each of the two operators. And what's going on here? So remember that so we get a two-point function of we basically get the product of two-point function. Here we can do the contraction like that or like that. And each of these is a two-point function of phi's, which we know is over there, and the p's just correspond to derivatives of the two-point function. So this is the first contraction, two-point function of phi's, and we need to differentiate it with respect to x1, j1 times, and then differentiate that with respect to x2, j2 times. So that's from contracting a pair of phi's, but there is still the other pair where we need to differentiate with respect to x1, n1 minus j1 times, and with respect to x2, n2 minus j2 times. Plus, I also have the other contraction, the other pair of contractions, which is, you just give us an overall factor of 2. So I'm just going to put a factor of 2, but you can check this yourself. Okay, so let's see if this gives us anything reasonable. It's like a bit of a mess, so let's just but at least it looks reasonable. There's some diagonal structure. Okay, well, this looks good, right? What do we expect? What we already seen is the structure of this Kronecker delta n1 and 2. It's a diagonal matrix, which didn't have to happen, but we know it. We know it should happen from conformal symmetry. And now, well, we can also see the correct powers of x1 minus x2, the thing downstairs over there. So let's divide by. Oh, when this happens, let's divide by that. Okay, so we are going to divide by what we expect to be the correct dependence on x1 and x2. So that's 2 times 2 delta phi plus n. Sorry, n1 in this case, because there's no n. Okay, so now we got rid of everything is diagonal, even for a 5 by 5 matrix. Okay, let's just try to guess this factor. So there is some -1 going on. So is there a way to get rid of the sound? Does anybody know how to get rid of the sound?
It's complicated because you're using autosave and this notebook is not saved anymore. If you save this notebook in, let's say, your desktop, it will disappear.
Ah, okay. If I save it, then
yeah, anywhere.
Oh. I never understood the purpose of it. It was just like always annoying me and didn't know what like. Thank you. Okay, now it's going to be much more flat to continue. So yeah, I mean I partially remember this answer, so it's not like I'm doing any black magic. So there's 4 delta phi, which increases. Okay, so I think it kind of increases like that. And then this is probably just some factorial. Yeah. Okay, so we determined this factor A. So let's call it the 2-point function of M1. The 2-point function. The next thing that you're going to need is the 3-point function, theCijk, between a pair of phi's and this double trace operator phi phi n.
The 2-point function is this or is it the inverse of this?
The 2-point function is this. Yeah, we computed. Yeah.
Are you dividing that?
Yeah, I was copying the 2-point function and then dividing by the 2-point function to get 1. So whatever I divided by is the 2-point function. Okay, the next thing that we need to compute is the 3-point function. So from conformal symmetry, we know that this should be some number which I'm going to call C phi phi n by slight abuse of notation times the answer by conformal invariance, which would be x1 minus x2. Now the dimension of this plus dimension of that minus dimension of that, which is minus n. x1 minus x3, which is dimension of this plus this minus that, dimension of that, which we already know is 2 delta phi plus n. And finally x2 minus x3, which is the same thing. Right. Okay, so first we can check, it's a non-trivial fact that it depends on x as follows, and we should be able to determine this number. Okay, so let's quickly do that. That's actually very similar to what's going on here, but slightly simpler. Now, now we are just doing a pair of contractions like that. Inside here, it's a normal order. We need to compute a product of 2-point functions with some derivatives inserted. So, okay, we just need one sum, a single m. We don't need to sum over 2j's because there is now only such one operator inserted. So we are summing over j. Only one alpha, because there's only one operator inserted. And there is each 2-point function is differentiated only once. So we have a contraction between x1 and x3 now. So x1 minus x3, which is differentiated j times with respect to x3, right? And then the other 2-point function is a 2-point phi between x2 and x3, which is differentiated and minus j times respect to x. And there's also a factor of 2 in this case because we can kind of permutate again. We can just choose which of the two phi's on the double trace operator we contract with. All right. So that looks quite simple. So what we should we should again check that the dependence on the axis is correct. So what I wrote on the board is x1 minus x2 to the power minus n, then x1 minus x3 to the power 2 delta phi plus n, and same thing for x2 minus x3. Okay, all the x's went away, so that's nice. But we are still left with some overall factor, which looks like okay, looks like a programmer of 2 delta phi n factorial. Okay. So what we learned, at least for this unnormalized double trace operator, the C phi n is that. Right. Any questions so far? Let's now go to the 4-point function of phi's. We'll be able to make an integral check of the formula, the 4-point function. So like I was saying on some previous board, this is a sum over conformal blocks. So like I was explaining in the previous lecture, this can be written as the product of 2-point functions, like conformal variance, times a function times some function of the cross ratio g, where the cross ratio is x1 minus x2, x3 minus x4, x1 minus x3, and x2 minus x4. And we can expand this 4-point function into conformal blocks, sum over I. So what happens is that you apply the OPE to phi, so you remember that the OPE, in general, schematically, this looks like a sum over I. I'm just going to put an upper index. Some of these operators are now in the 3-point function is basically C phi phi I, where these two, the upper index and lower index, are related by the 2-point function, right? If we compute the 3-point function of phi phi with O, and you apply this OPE, assuming that delta ij is something like that, so some normalization A. From here, it follows that we can compute the C phi phi I as AI and the C phi phi given an upper index. So what we are going to find here is the following. When you do an OP of two T operators in this generalized B field, the only kind of operators that we can generate are the identity and the double trace operators themselves. Somehow the number of T's is conserved up to generating lower orders of T. That's because of normal ordering that you can generate. If we normal order this, you only get the double trace operators. If you do not normal order that, you get identity plus the double trace operators. And so what we should find is the contribution of the identity conformal block, with dimension 0, plus sum over n. And remember now the n's are only even, so it's like that, times the C phi phi n, C phi phi n. So this is from the OPE. and then the rest is a 3-point function. So it's a product of the upper and lower index times the conformal block of dimension 2 delta phi plus n, which is the dimension of this arbitrary operator. So this is a equation that should be valid, and we already computed both of those two things because we computed C phi phi n and we computed the an. So let's see what we get for the 4-point function. So this calligraphic G and S. This 4-point function should be the. Let me first define the conformal block, which I was calling G, which in this case of equal external dimensions, all of the dependence on the external dimension drops out, and you only get a rather simple looking formula. It's a hypergeometric function. It's as follows. You can check it against the previous formula. So this is the block for equal external dimensions. And so what we have, what I explained is that you got the contribution of the identity block, which, by the way, is just 1. Because in that case, the series expansion of hypergeometric truncates. So the conformal block of the identity was only 1 because identity has no global descendants. And then plus, we should have a sum from well, n, 4, and so on of this 3-point function, which was defined to be defined as to be the 3-point function that we computed before. And the coefficient in the conformal block expansion is the square of the 3-point function divided by the 2-point function. So that's the same thing, the product of an OP coefficient and the 3-point function. The OP coefficient is a 3-point function divided by a 2-point function. Alright, so this is what we computed, and it's some quantity, which, by the way, this minus 1 to the n doesn't matter because n is even. Better, and we are summing over from n to some n max with steps of 2. So this is how you tell mathematically that you should sum with steps of 2. And what you are summing is the conformal block with dimension 2 delta phi plus n. Now this should be a convergent sum, which is an expression for the 4-point function, which is a rather complicated way of writing a rather simple object, because we already know that the 4-point function is just a sum of 3 reconstructions. You can compute this because it's a Gaussian theory. You can either construct like that. There are 3 reconstructions: 1, 2, 3, 4, 1, 3, 2, 4, 1, 4, 2, 3. And it can check for yourself that these 3 contractions will look as follows. So the contraction 1, 2, 3, 4 is just a product of 2-point functions, which we, however, took out of the G. So this just gives us 1. Then the second term is precisely the definition of the cross ratio. So it gives us z to the 2 delta phi. And then the third term is some permutation. And it's the same thing as a cross ratio up to a permutation, which basically switches 2 and 4. And you can again check that under switching x2 and x4, z becomes z over 1 minus z. That's not right. Well, anyway, the words were not correct, but the formula is correct. This comes from that, this comes from that, this comes from that. So now we have 2 different expressions for the 4-point function, which is this one, and on the other hand, this is an infinite sum over conformal blocks. And if I didn't make any mistake in Mathematica, they should agree with each other. The the identity block correctly gives us 1. So the rest of the sum should give us this sum of these two terms. The nice thing is that you can, effectively, you can just proceed order by order in Z. And you can already see that the structure is more or less correct because the block, let me remind you that the block, the conform block, basically looks like a power of Z times some function which is regular at the origin. So you can think of the block as some kind of fancier version of Z to the delta. So this looks like expansion in powers of Z to the 2 delta phi plus n, which indeed has the correct structure as these two terms, because both of them go like Z to the 2 delta phi as Z goes to 0 times some infinite series in Z. So let's just check this, that we didn't make any mistake. Let me get rid of that. So yeah, let's just look at the sum. Up to say some order 10, and look at its series expansion around small z. Yeah, to order 6. So far, this okay. This looks a little messy, but we haven't simplified. This looks much simpler, and if we didn't make any mistake, then this should be equal to the z over 1 minus z to 2 delta phi plus z to the 2 delta phi. Yeah, okay. So the series works. So we can go to all the way up to order 10, and it's still correct. Now, what changes in the fermionic theory? I remember at the end of the last lecture I mentioned the general space fermion, where we still have the only thing that's going to change is that there is a sign of x1 minus x2. Then here, so imagine phi is a fermion, which sounds unnatural, but I don't want to rewrite everything in terms of C, but imagine it's a fermion. Now for the fermion, alpha j should be alpha and minus j, so minus alpha and minus j. So n is odd, but everything else, all the formulas are correct. We should take n odd, and in the formula for the 4-point function, the only thing that changes is an extra minus sign here, because we have 3 contractions, and this is the only contraction where the 2 contractions cross each other. So this means that we should get a minus sign here. Now the spectrum for the boson. I'm just going to remind you, for the boson, the spectrum was 0 from the identity, and then 2 delta phi plus 2j. And for the fermion, the spectrum is an identity, and 2 delta phi plus 2j plus 1. J 0, 1, 2, and so on. Okay, so we just can make the same check. Which is basically a consequence of some symmetry of the blocks under z goes to z over z minus 1. Can be a bit lowbrow, and just do a sum from 1 to 10 with steps of 2. And the only thing that should change here is that there should be a minus sign, and it works. Okay, very good. And 45. Okay, so yeah, are there any questions so far about generalized free boson, generalized free fermion, and the principles of the 1D bootstrap? These are sort of boring theories because they are free, but Boostrap can teach us much more, and it can teach us some general bounds. You can use it to prove general theorems on any conformal filter, whether it's interacting, or even if it's very strongly interacting, they will still be valid, and that's what the rest of today will be about. And then next Friday we are going to see how some of by the end of this lecture, we are going to see how some of these bounds can be sharp. And in fact, one of them is exactly saturated by this generalized fermion, which is why I went to some length of explaining this here. And in the lecture next Friday, we're going to see how this sharp bound on the CFT data, which is saturated by the free fermion, is exactly equivalent under a certain mapping to the exact solution of the 8-dimensional and 24-dimensional sphere backing problem. And we will be able to do that by essentially uplifting some technique from the conformal field theory that I will discuss today in the rest of the lecture. So the general idea, I keep losing the nice charts. Yeah, so the question is, what can we learn on general grounds learn about this set of CFT data, the deltas and the CIJKs, in any unitary CFT from the Boostrap equation. And actually, it seems like we can learn a lot. There's been a huge industry in the called the conformal Boostrap program, which started in this form, and I'm going to explain it in a classic paper of Ratate, Richcottoni, and Vicky. By now, it was 16 years ago. I think it's 2008. Their motivation was actually four-dimensional. They were trying to constrain some conformal models of four-dimensional particle physics. But this program has been since applied to various other cases, most notably the three-dimensional Ising model, for which a couple of days ago there was in fact a huge improvement in the precision in our knowledge of the scaling exponents. People were able to kind of shrink the allowed region by about a factor of 50. And it's at the moment the most precise way of determining critical exponents in the 3D Ising model and various other. Oh, the new trick was that they edited stress tensor. So the original work, and then the work by Slava alone, and well, with some Duffin, Miguel, and various other people, they started by looking at the 4-point function of sigma. Then later, I think about 10 years later, people were able. So I think this was 2000 maybe 2011. Then so basically these are like all the 4-point functions involving sigma alone. Then you can look at all the 4-point functions involving the sigma field and the energy field. The Ising model. This was I think 2017. Philip Cosdale, and Davidson and Duffin, which already beat Monte Carlo. And what they did a few days ago is that they added the stress energy tensor, which is another conformal parameter. I'm not going to discuss these works in detail because I'm focused on the one-dimensional case. These works are numerical, and they're extremely impressive and very teaches some deep things about conformal field theory, but you cannot prove any of these things exactly analytically in 3 dimensions. Well, for example, nobody has been able to determine the delta sigma delta epsilon analytically. I think probably using this method or otherwise. But in 1D, it's a situation where you can prove various things. You can prove the sharp bound analytically, which is what this is. But this is getting a little bit ahead of the lecture. Right, so remember that the set of constraints that we started with in a Boostrap is labeled by quadruples of conformal primaries and some cross ratio z, which is really a huge set of constraints. But in the rest of this course, I'm going to focus on a simple section of those constraints, relatively simpler section of those constraints, which is where we set all of the 4 primaries to be the same. So I is j. So this is kind of the analog of the first work in the 3D Ising involving sigma alone. So we are going to be studying the consequences of crossing symmetry of a 4-point function of identical fields. So let's. I'm just going to write this in a slightly different way than before. Before I was taking out a 2-point function 1, 2, 3, 4. So now I'm going to do 1, 3, 2, 4. And correspondingly, instead of G, I'm going to write G twiddle here, where the OPE gives us 2 different formulas for G twiddle. The I equals 0 term always for me is meant to be the identity operator. So the reason to change the definition slightly to put 1, 3, 2, 4 is that now this factor is invariant under z goes to 1 minus z. That's because you take z and you change x2 with x4, then you get 1 minus z. And this operation leaves this prefactor invariant, unlike with in the previous case, like at the symmetry. So basically, we want to study the consequences of this equation. And the way to leverage this equation, some of the main point, is that you can ask, what are the spectra, what are possible sets of delta i's which are compatible with this equation? The reason why this is constraining is that if somebody gives you some randomly chosen spectrum of delta i's, you can view this as a set of linear equations for the C phi phi I squared. But because C phi I is real, this square is positive, and it may very often happen that this equation for a given spectrum just does not have a solution with positive phi phi phi, with positive factors. So this is the reason why this equation can constrain the possible spectrum. And in particular, what this equation implies are upper bounds on delta 1. So the first non-zero delta in this sum. Now, if all of the operators have two large scaling dimensions, there is just no way to solve this equation while maintaining positivity of T phi I squared. Okay, how are you doing on time? Let me just write some functions. So let's define. Let's cast this as a vector equation in some vector space. So let's define f delta phi delta of z to be this anti-symmetric combination of conformal blocks. Essentially, what we are doing is that we are subtracting the right hand side from the left hand side, and then that equation in the box is the same as the statement. Let me separate the identity. So the identity looks like that. And from 1 to infinity. Oh, I should mention that one of the authors of that amazing paper from a few days ago is in the audience, Rajiv.
Yeah, questions?
Yeah. Yeah, so the equation in the box now becomes this equation. And the way to think of this equation is that f of z are some vectors, some very specific vectors in a vector space of in some function vector space. And this just tells us that we can sum the vector corresponding to identity with some other vectors with positive coefficients to get 0. This may not always be possible. The reason why it may not be possible people cannot see where if I write it here. Imagine this is we take some two-dimensional projection of this infinite dimensional vector space of functions of z, and let's imagine that the identity points in some particular direction. So this is the f0. I'm suppressing the delta phi label, and the z label becomes the directions in this plane. Let's imagine that all of the other vectors in our chosen spectrum lie in some half plane, in the same half plane as f0. Then clearly it's not possible. This is delta 1, delta 2, delta 3, delta 4, and so on. Even if you put infinitely many of them, it's just not possible to solve this equation simply because they're opening in the same half plane. So you can find a line which separates them all from. Right? That's a very simple idea. To make it.
No.
Sorry, a few more people. I'll start speaking slowly and writing slowly. Yeah, so let's just see that what I just said is true. That indeed there is such a situation where we can prove spectral bounds by showing that all of these vectors lie in some half plane, in the same half plane or half space as the identity. For that, it is useful to choose a particular projection of this infinite dimensional vector space. So let's see what this is. In principle, this equation holds when z is real between 0 and 1, but in fact, it can be unreal continued, and it holds more generally when z is complex, away from two branch cuts, which are essentially the branch cuts of the conformal blocks. So this the function g has a logarithmic branch cut starting at 1, going to infinity, and it also has a parallel branch cut starting at 0, going to minus infinity. Kind of looks like that. And the second term is just a reflection around equal 1/2. But notice the equation is anti-symmetric on this equals to 1 minus z. So we can systematically study it by Taylor expanding it around z equals 1/2. So this is just a natural choice of the coordinates in our vector space to be just the odd order derivatives of the vectors of these functions at equal 1/2. Let's do that. Let's define the little f with now subscript n. Superscript delta phi is just a parameter in this whole story, and now I'm going to put delta to be variable like as such. Let's define this to be the nth derivative that's equal to 1/2 of the function capital F at z. Okay, so now the equation that we are trying to solve are that for each for each n odd, n positive, any valid CFT must satisfy these constraints. There's an Fn delta phi at 0, which is the identity, plus a sum with positive coefficients we're going to see TVI squared of the n component, call it the delta I, and this must be equal to 0. Okay, and then so these given values of n are just the different projections of the infinite dimensional equation. And well, how do we prove an upper bound on delta 1? An upper bound on delta 1 is produced by following simple proposition. So let's imagine, let's fix n to be some positive integer. So we are going to truncate that equation to some finite limited derivatives. And let's imagine that we can find a linear combination with some coefficients, let's call them beta m, of these odd order derivatives. So we are starting at n equal 1, so this should be 2n minus 1, so that this starts at 1. Okay, so let's imagine we can find the coefficients beta n such that this function, so defined, satisfies that omega at the origin is something positive, let's say 1, and such that omega delta is non-negative for all delta greater than some delta star. Then for all CFTs, maybe there's no line. For all CFTs, delta 1 must be less than or equal to delta star. I mean, that's kind of obvious. If you how do you prove it? Well, we prove it by first noting that for such omega, by applying these identities, omega 0 plus I zero is just a consequence of the crossing equation. Now, but not by property 1, this is equal to 1. By property 2, this is positive everywhere above delta star. So there has to be at least one term in the sum which is below delta star. Okay. Delta 1. And now let's see that this is actually effective, that this can work, and that we can find such coefficients that produce some non-trivial upper bounds. Just to make sure that I have enough time to cover everything. So let's define this little f. It depends on delta phi and delta, and it depends on the order of the derivative. So this should be the conformal block G delta phi delta. Is this how? No. Sorry, there's no delta. There's this prefactor that I forgot about. And you want to take a derivative of this with respect to z of order n. Now, if n is odd, I can forget about the second term. The second term is minus. It's symmetric, right? It's anti-symmetric. So if the derivative is an odd order, I don't have to write that term. I'll just get a factor of 2 here. Just we can forget about factor of 2. And we want to evaluate this at z equals 1/2. Okay. So now let's let's look at the projection under the first two components, just like I did before, schematically on the board.
Sorry,
Yeah.
this doesn't seem to depend on delta.
Oh, that is correct. That's because there is a mistake. Thank you. If now it's better. So these are the two. These are the first two components, the first derivative and the third derivative. And let's see how it actually looks like. So we can do parametric plot. Now this just plots the two coordinates as a function of delta, starting at 0, so yeah, going up to 5. Now this will just show how this vector evolves as a function of delta. And I'm going to set delta phi to be some nice constant, like 1/2. This actually maps to the 8-dimensional sphere packing later, and 3/2 will map to the 24-dimensional sphere packing. What does this look like? Well, it's kind of ugly because the two components evolve at different rates. So it's the aspect ratio to 1. It's a little bit too large now. Okay, so it's kind of similar to what I was plotting before. This is where the identity sits. If we go to higher delta, it's still not very good. Just make it more visualizable, I think. I seem to remember it's working. I'm just going to plot a certain range of this plot so that it looks nicer. That's much better. So this is where the vector starts at identity. As we keep increasing delta from 0, it kind of evolves like that, goes up, go out, and then starts going down. So you can see that at some point, once we impose the gap, for example, around here, you can certainly cut the picture through the origin so that the identity and everything above the critical delta is in 1/2 plane. So this shows that there is an upper bound on delta. Now, of course, this corresponds to the proposition because a half plane here is like a choice of an element of the dual space, which is precisely choice of these betas, right? These betas live in a dual space, and we want to choose such an element of a dual, so that when we take an inner product or we apply it to all the vectors, which is identity and everything above a gap, then we get some positive answer. Now, in the critical case, we want to minimize here. We want to minimize delta star such that 1 and 2 hold, which is like basically minimizing the location of this point, such that it exactly kind of lies on the same line as the identity and the origin. So in this critical case, actually, this element of the dual space, it doesn't want to be strictly positive on the identity. It wants to be 0 on the identity. In general, you would find some dual vector that looks like that, where the identity is positive, but in a critical case, it collapses to 0. So we can just do that. So in the simple example, the element of dual space is like a linear combination of the third derivative and the first derivative. This coefficient beta 1. Now I'm telling you that this at large delta, both f, I think this one and this one are positive. So positivity at large delta is equivalent to just choosing the coefficient of f3 to be positive. So we can just choose it to be 1 by overall rescaling by some positive number. So what we then want to do is to find its critical beta 1 such that it vanishes at identity. Okay, so let's just set delta equal to the identity. This gives us an equation for beta 1. And now we can plot this functional as a function of delta. let's say up to 5. Okay. So this is what it looks like. And well, what is this? What is this functional? This function is precisely the dual vector which is 0 here and 0 here. Right, so you can see it's not very visible, but from here it kind of curves a little bit upward. Then it curves and it starts curving down. And it looks like at first the function should be a little bit positive, then it's going to dip below 0 until it hits here, which is where it's going to become positive and stay positive forever after. And this is indeed what you can see in this picture. First it starts at 0, then goes all the way positive, then it's certainly negative, and then it just is positive forever. And from this we get our first rigorous upper bound on delta 1, which is the location where from which it's positive forever after, which is its first 0. So let's find this now. Okay, these equations as a function of delta, they are kind of ugly, but you can find the root. Now, in general, let's if we set delta phi to be 1/2, then you can see that this root is somewhere between 2 and 3. So let's say we are looking for a root close to 3. It's about 2.44. So what we have shown is that for any CFT, the OPE of two operators of dimension 1/2 needs to have, besides identity, another operator whose dimension is less than this number, 2.44564. And this is rigorous. Even though we truncated the full equation to some finite dimension, we are still using valid constraints. Both the identity coming from the first derivative and from the third derivative are completely valid, rigorous non-perturbative constraints, and we just found a linear combination which has these positivity properties. So this number is indeed a completely rigorous upper bound on delta 1 in any CFT. Okay, so what appears in the 5i OP in any CFT in any dimension, because you can restrict your operators to lie on it. So to always lie on line. Actually, let's define. Let's find it as a function of delta phi. So the bound is going to depend on delta phi. Let's also depend on some precision. And I'm going to save it every time it's computed so that I don't have to recompute these bounds. Now, it turns out that the bound is relatively close to 3 delta phi, so I'm kind of cheating here. So this argument tells the function find root where to start looking for the solution. So I think it's around 3 delta phi in general. And we want to work to some precision. Let's see what this bound looks like for some precision 30 as a function of delta phi. You can start around 1/10 and go to 3 with steps of 1/10. I'm just going to compute points where on the x-axis there is delta phi, on the y-axis there is the bound, and just to make sure that it doesn't run slowly, let's see how fast this bound.
1/101 instead of 1/10.
Oh, okay. It's gonna take a little bit longer. Also, I think I want to, because the output of find root is it's some list. What I want to do, I think, is I want to take the first element. I mean, this just produces the actual number. Okay, and let's look at what it looks like. It doesn't look very good. I think this is what it's supposed to look like. I think the problem. Oh, sorry. This is wrong because you see what's happening here is that this procedure doesn't guarantee that I find this root, but I may also find this root. So that's actually what happened here. That over here I have the correct root, and over here it actually found this root. So I'm going to just add 1 for the starting location. This. Yeah, okay. Now this looks much better. What do we? Okay, what do we? By the way, let's see what this bound does when delta phi becomes small. Okay, it's kind of close to 1 here. Okay. It gets very close to 1. So as delta phi decreases, the bound seems to be getting close to 1, which and we know a theory that lives there, which is the geometry fermion. That for the geometry fermion, which is a solution of this equation, by the way. So the geometry fermion is the solution of this equation with the spectrum 0 and 2 delta phi plus 1, 2 delta phi plus 3, and so on. Oh, with positive coefficients, which you can see from here that these coefficients are positive. So the gap, so delta 1 for the geometry fermion is 2 delta phi plus 1, which goes to 1 as delta phi goes to 0. And the bound that we found also goes to 1 as delta phi goes to 0. So it seems that the fermion, at least in this limit, was saturated. Let's just compare our bound with the geometry fermion as a function of delta phi. One, plot 2. I'm just going to plot the answer in the geometry fermion. Delta phi plus 1 from 0 to 3. And then I'm going to superpose these two plots. So the free fermion is the blue line, and our bound, which is true for all theories, are the dots, and the fermion is below the bound, and it gets saturated in this limit. So that's nice. But remember, we can improve the bound because we've only used 2 components so far. We have used this proposition for rather small values of n, which is n equal to 2. And the question is, what happens to this optimal upper bound on delta 1? What is its optimal delta star if we increase capital N?
Is it always guaranteed that you will find an omega for finite n? Or maybe in some cases you need to go to, let's say, infinite n, that you can find this omega that satisfies 1 and 2.
For a large delta star, generically, if you make delta star large enough, then you can find it for n. Well, you need n at least 2. You can't do it for the single one. Essentially, what? You just need to make sure that one of them dominates at large. What are the conditions? I think if n equals 2 already, you can always do it if some inequalities are satisfied. Okay, so let's denote delta star n to be the smallest delta star, such that 1 and 2 hold, or really it's the infimum, because I'm imposing the condition 1 with 1 instead of a 0, so this will not be totally saturated, but if we allow this to make it smaller and smaller all the way down to 0, then it can be the minimum, such that 1 and 2 are satisfied. In other words, delta star n is the optimal upper bound on delta 1 if we work in this n-dimensional vector space. As n increases, delta star is a decreasing function, So it gets better and better, the bound. Decreases as n increases. And the question is, what is delta star infinity? So what is this optimal upper bound coming from the full power of the Boostrap equation? If you do this numerically, so this is some linear program. It's a finite dimensional program. It's infinite. It's a continuum of constraints. But you can solve it more or less systematically for any value of n. And what you find that it looks like the delta star n. There was some numerical evidence that this converges to 2 delta phi plus 1. So that in fact, for larger values of n, all of these dots will come down. As you increase n, it's going to go until it hits. It cannot go anymore beyond the curve. Actually, the free fragment will saturate this optimal bound for any value of pseudo delta phi.
How is it that you find an optimal bound by looking at just one 4-point function?
It is. Well, there's no reason why it couldn't work. It's lucky that it works. Yes, I agree, it's lucky, but it works. And it's kind of similar in the sphere packing. You could ask, how come that the 8 or 24-dimensional sphere packing could be solved using protocol? It's also one. Yeah. Yes, because I raised a proposition, but if you increase n, you're giving yourself more freedom in constructing linear combination. So conversely, if you decrease n, that's like specializing to omega delta, where some betas are 0. So maybe let me say what happens typically. Yeah, like until 12 or 12.
You need 5, 10 minutes more, or?
Well, I need more than 5 minutes from now. I'm just not sure what's the I don't know what's the usual like.
15 past 12.
That's great. Yeah, okay, let me actually say a little bit more about the finite dimensional case. So the reason why for a given capital N you cannot improve the bound anymore is that there is actually a solution with positive coefficient with that given gap. So let's just make this a little bit more precise. Let's set n to be even and take n to be n over 2. Then this means that what we are imposing are these constraints. For all n between 1 and capital N. And you can think of these as n equations in n variables. So it's a solution with n variables, which are these n over 2 delta I. So there's a solution with n over 2 operators. The variables are the n over 2 delta i's and n over 2 di's. And the reason why delta star n cannot be improved any further is that there actually is such a solution with with positive DIs. But that means that the optimal, well, let's construct the optimal functional with this optimal omega is some linear combination of the, let me call the optimal functional for capital N, omega n is omega n. Coefficient of beta, 2n minus 1, delta phi delta. So this, so the optimal functional should be 0 at the identity, and it should be positive for all delta above delta 1. Where now delta 1 is this delta 1 which appears in some particular solution of this truncated system. But the fact that we have an actual solution of a truncated system means that we apply the functional to the equation, we get omega n. Because there is an actual solution of this equation. But now, since all of the additional deltas are above delta 1, this term is 0, and all of these terms are non-negative. They actually all have to vanish. This is very similar to what we saw, for example, in lecture 2, when we were looking at we were able to find the limit cycle of the Van der Waals oscillator by a very similar argument. There was some kind of a functional, which was the oscillator function we were constructing, which was non-negative everywhere, but because it was producing a bound that was saturated by a certain trajectory, the function actually had to vanish on the trajectory. So in this case, the analog of that oscillator function that we were constructing is omega, and the analog of the trajectory is the spectrum of delta i's. So just from these two constraints, it follows that omega delta I vanishes for all I appearing in that solution. But in fact, assuming it's a smooth function, also its first derivative has to vanish for all I starting at 2. Right, that's you can see. So there's imagining delta 1, delta 2, delta 3, and so on. So the omega is 0. The omega is 0 over here, and it needs to be non-negative everywhere to the right of delta 1, but it also has to vanish here and here. So these positions better be zeros of even degree. So typically this will look like something like that. No matter what this function is, it needs to satisfy for the optimal upper bound on delta 1 at a given time. Now, this is kind of a crucial point. Yeah, so you can have the first equation is a statement that there is a solution containing n over 2 operators of the truncated system, and the solution is the reason why the upper bound cannot be improved any further. It's a kind of linear programming duality. But if you cannot improve a dual solution, somehow the omega is like a dual solution, the fact that you cannot improve it means that there is a solution of the primal problem. So that's the primal solution, and this is the optimal. This is the optimal solution.
Yeah, it's OP coefficient square.
Yes, the DI is OP coefficient squared. Yes, I was.
So why on the n/2 operator? The property of the free theory?
No. No, it's not a property. The free theory has infinite many operators, like in a CFT, and even in this OPE. But if you only impose the first capital N equations, this is just it's just N equations. So it should have, roughly speaking, a solution with N unknowns. And here the unknowns are the N/2 deltas and N/2 D's. So the counting works.
But these delta I and I will not correspond to A, given CFT, but they solve this
Yeah.
equation.
But as N goes to infinity, they will start corresponding closer and closer to an actual CFT, and that brings me to the punchline, which is a theorem, and the theorem says that that I already wrote on the blackboard, delta star N indeed goes to delta phi plus 1. In other words, the generalized prefermion saturates the optimum bound on delta 1 for all delta phi positive. Or in other words, for all CFTs, I mean this is the equivalent, for all CFTs, delta 1 is less than or equal to delta phi plus 1. And this was first proven in 2016 for delta phi, which are integers or half integers. And then together with Miguel Paulos, he extended it to all positive delta phi. And for lecture next week, we'll see that for delta phi 1/2 and 3/2, this theorem is the statement of the optimal sphere backing identity. In the remaining time, I'm going to prove this, at least for the two cases that are relevant for sphere packing, which is delta phi equal to 1/2 and 3/2. And the point is that, okay, yeah.
Just if you take this important and go into infinity, and you know all these deltas, for delta phi plus 1 plus 2j. So what is this function?
That's what I'm going to explain the rest of it. That's how you prove it. I mean, you have to construct the function. Okay, maybe I should. Yeah. So what's the idea? So we already know that delta star infinity has to be bounded from below by 2 delta phi plus 1, because there is a solution of the crossing equations with that gap. Right? The generalized prefermion has this gap, so the upper bound can never beat that, because it will be in contradiction with the generalized prefermion. So you know this automatically. So what remains to be shown is to construct omega, which certifies that this is the bound. What we need to show, what we need to construct, is a functional whose zeros are 2 delta phi plus 1, 2 delta phi plus 3, 2 delta phi plus 5, and so on. So But now this function really has to include all of the derivatives, not just a finite number of derivatives. So it's better to think of it abstractly as a linear functional on some vector space of functions which are holomorphic. Which are holomorphic in this cut plane, which is where the equation is satisfied. And let me denote omega delta to be I'm defining this to be the action of the functional of this thing on our original vectors. Right, so these were some functions of z, so I can apply omega to them, and I get a function of delta, and I'm suppressing the delta phi. So you can just think of omega as a function of delta when it acts on this vector phi. And what we need to then what needs to be satisfied is that omega 0 is 0, omega delta phi plus 2n minus 1 is equal to 0 for all n that. And the first derivative vanishes. There's a second order 0 for all n 2, 3, and 6. There's also an important technical condition because now we are working in some infinite dimensional vector spaces, so we need to be careful about continuity. Essentially, we need to make sure, that whenever we have a solution of the Crossing equation, then from this we can actually deduce that we can swap the action of the functional with this infinite sum over I. This was otherwise been satisfied for the omegas we were using before because they're finite combination of derivatives and all of the left-hand side converges in that case. But if we work in this general function space, we need to be more careful that actually omega is continuous in the appropriate function space. So this was pointed out by Ritkov and Jia Shin in 2017. So a little bit later than my proof, but actually the thing I constructed satisfied the constraint, so everything was good. Okay, so the problem, this now became some problem in analysis. I'm going to construct a linear function of omega, such that if you apply this to these special functions f, which are some hypergeometrics in them, then as a function of little delta, you get these properties. And it turns out that these properties fix that linear function uniquely. So you don't have to impose positivity anymore. Positivity just comes for free. That any linear functional that satisfies this and the condition star, there is just one of them, and you can show that it's actually positive. So that will complete it.
Sure. Can you repeat a little bit about this continuity condition? This is so omega. You need to be continuous in delta. Is that the
No. Omega needs to be sort of. It just means that if this was a finite sum, this is obvious, right?
Yes. Okay.
So you need to be careful if it's an infinite sum, then you can still do it, which means that imagine you have an infinite sum and just look at the tail of the infinite sum and apply omega to the tail. So you need to show that as the tail becomes smaller and smaller, acting with omega on the tail comes to 0. That's continuity. The way I say it is continuity at the origin, but it's equivalent proof to continuity. Yeah, I didn't tell you what the norm on this space is. It's just easier way to formulate is this, right? For any solution of this equation with positive coefficients, you need to prove that this is true, kind of abstractly. So that's what, and these people explain what are the conditions on omega. So this is. So we are continuing with the proof by construction of omega. And so now I'm going to explain it the way that it was presented in my paper with Miguel from 2018. And this amounts in choosing an ansatz on F, which is quite natural, although at first sight
Communication générale.
we were choosing omegas to be finite linear combination of derivatives around z equal 1/2. Well, let's now choose something slightly more general, which is contour integrals. And well, what are the natural contour integrals for this problem? The special points are 0, 1, and infinity. There is a symmetry between 0 and 1 because the problems of undisymmetric under z goes to 1 minus z. So the special points are kind of 1 and infinity. So let's just write this ansatz, where so the ansatz for omega f is a general function which is holomorphic in this plane, which is anti-symmetric under z goes to 1 minus z. So almost regardless of generality, you can write any reasonable functional as a sum of two terms. The first term is a contour integral from 1/2 to 1 against some function a, which parameterizes the functional, and you can say this is parameterized by a and b. And the second term is a contour integral from 1/2 to infinity, 1/2 plus I infinity against some other function b. So this first term is this little segment, and the second term is the big segment. And now our task is to determine a and b such that these conditions are satisfied, and then we'll win. And also that this condition is satisfied, I should say, okay, I'm going to state without proof that this condition star means that b of z should be of order z minus 1 minus epsilon as z goes to infinity. And I'm forgetting what it is on A, but I think that it's basically should go like z to the probably 2 delta phi minus 1 plus epsilon probably as z goes to 0. Right. The 0 and infinity are the problematic regions because it goes to 0 and goes to infinity and goes to 1. The OP converges slower and slower. Okay. For generic value of z, it converges like an exponentially fast, but goes to these points, it stops converging exponentially fast. So you need to be careful if your function is probing those regions. You need to be careful. It decreases there sufficiently fast so that you can so the tails of the OP sums go to 0. But okay, if you didn't follow these comments, just read this paper and just remember that these are some asymptotic constraints on B and A. And so what we want to do is to use some contour manipulation to bring this function to the following form. So let's now act not on a general f, but on the special functions f given by the hypergeometrics. And the claim is that if we choose a and b correctly, then there is a contour manipulation which brings this action of the function on these f's to the following form: cos squared pi over 2 delta minus 2 delta phi. This is order looking good. Integral from 0 to 1 of a z, and essentially the astronaut conformable here. So d to the minus 2 delta phi conformable g dz. So the same omega, which we'll fix uniquely, can be brought into this form, where now there's a prefactor that has the correct double zeros. So this thing has double zeros whenever delta is 2 delta phi plus an odd integer. And now g, it will turn out that a of z is positive for all z between 0 and 1, and a of z goes like z to the minus 2 as z goes to 0. So now, when delta is big, this integrand goes like, as z goes to 0, this integrand goes like d to the delta minus 2 delta phi minus 2. So when you integrate it, produces a simple pole at 2 delta phi minus 1. And the simple pole makes the double zero at delta equals 2 delta phi plus 1 into a simple zero. But above, when delta is greater than 2 delta phi plus 1, the integer will converge and be manifestly positive. Are you with me?
Symbolic behavior is it coming from the box formula in the lower box? This integrand, when z goes to 0, you roll down z to the delta minus 2 delta minus 2. Does it follow from the result by Slava and Jiaxing?
This. No, it doesn't follow. I'm saying things not out of order. So I'm going to find A and B, which do the job. And what does it mean that they do the job? Why do they do the job? There's a contour manipulation, first of all, which brings it to this form. Also, they satisfy this, so that they are good functionals in general. Furthermore, A that I'll identify will satisfy this condition and this condition. And from these conditions, you get those equations, right? And you get omega delta being positive or all delta above 2 delta phi plus 1. Because this integral, this representation only works when delta is greater than 2 delta phi plus 1. The first representation works for any delta, but you can only make it manifestly positive when delta is greater than 2 delta phi plus 1.
The question is that had your conditional field box, then you have
sorry. Sorry, I think this should. Sorry, I think this should be 1 minus z. Yeah. Sorry about that. I mean, in the end, A and B are connected to each other, so you can just forget about A, just work with B. Yeah, sorry, this is correct. This is 1 minus z. As z goes to 1. That doesn't make sense because you're integrating. Oh no, it's fine. Sorry, we are integrating a from 1/2 to 1, so we don't care about what happens at 0. For this condition, we care about what happens at 1, and it's that. Then there's a contour manipulation, which by holomorphic you use. So you get this, and then this condition will guarantee that this formula can be used for delta greater than delta phi plus 1. This is positive. This is the zeros. Now this thing has a pole at 2 delta phi plus 1, which is a simple pole. So it cancels the double zero, make it into a simple zero. So the structure is exactly like
The relation between A and B, or
that. It's coming. Yeah, first, I'm saying.
and this is the final statement you're going to.
But I want to motivate like what do we want from A and B before I actually find it.
Contour modification.
Yeah, that's all that's coming. Okay, so what's the contour modification? But maybe I should say this more clearly. So far, we need that A of z is a further 1 minus z with 2 delta phi minus 1 epsilon equals to 1. That this like that is equal to I infinity. and that A of z is basically, it must be equal to some A for A0, but it literally goes like z minus 2. Okay. But I haven't explained to you how to go from here to here, which is what I'll do now, and that will produce some additional constraints on A, B, which will be sufficient to find a unique answer for A and B. And the only condition, the only non-trivial, you may think this will depend on some non-trivial properties of the conformal blocks. But in fact, actually, the only thing that you need about conformal blocks is that if you analytically continue them, so this is 0. If you take the conformal block and analytically continue it to negative reals above the branch cut, well, what do you get? There is some phase which must be this one, right? Because the conformal block looks like z to the delta times something regular. So the phase is e to the I pi delta. And what you get, multiplying it, is actually the conformal block that transformed z. I mean, this is because this is a hypergeometric function, the solution of a second-order differential equation, and a differential equation has this z goes to z over v minus 1 is an exact symmetry. So this is a symmetry of the hypergeometric equation, which means that there is a unique solution with a given leading behavior. If you sort of fix the leading behavior, and so this is just a consequence of that symmetry. Right? If I go to the on top of the branch cut, I find that this is the overall constant, and this thing is a solution of the same differential equation, and the two sides have the same asymptotic behavior as e goes to 0. Or you can just check it explicitly. But this is some symmetry which preserves, this fixes 0, 0 goes to 0, and something slightly positive goes to something slightly negative under this operation. All right, so now let's do this contour manipulation that I keep promising you. So let's take our ansatz for omega and act on this f. Okay, this f is the difference of the one block minus the other block, which is equals to 1 minus z. So let's just unfold all of this. First, we have the first term, which is an a. Then you have the second term, which comes from the reflected guy. Let's change variables in the reflected guy to bring it to the same form. We get a minus. So I change variables from z to 1 minus z. Basically, we change variables everywhere so that the same block appears. Then we have the b integral, which is from 1/2 to 1/2 plus infinity. And the final term will come with a plus because I'm not going to flip the integration bound. So now it's from 1 plus infinity, and this one is from 1/2 to 1/2 minus infinity. Okay, so this is just a simple rewriting of the previous definition. Nothing special happened. Let's just see what goes on. This is the first term. This is the second term. This is the third term. And this is the fourth term. And what we're going to do is that we want to bring it as close as possible to this formula over here. And you see this formula is going to, this underlying object is the same thing as 1 plus cos I delta minus 2 delta phi. Right, this thing oscillates, this thing shifts it to 1. So the 1 will come from these two terms, and the cos will come from these two terms by rotating the contour to the branch cut to negative z's, where we use this identity. So this identity is going to produce for us precisely the right phase, which will produce this cosine.
Why do the B turn into A's?
Well, that's good. For this to work, A and B need to be related. Because all of it, ultimately, the integrand only involves A, which means B is fixed in terms of A to be something. That follows from being able to combine all these things in a consistent manner. I can go more or less through all the steps. Okay, so we'll just keep manipulating. Let's first extend this integral all the way to 0. Okay, let me call this thing. Let me just call this little g of delta, but I don't have to keep writing it. Okay. But now I added the part which goes from 0 to 1/2, so I need to subtract it. And I'm going to combine that subtraction with the second term from the previous line. So I get A 1 minus z. Actually, let me keep that open for now. And now I'm going to take these two terms and rotate the contour like that and like that, which means I'm going to end up with some little pieces that stretch between 0 and 1/2. So I can also put them in this side, right? So it's minus bz from this one because the contour goes left, that's why minus, and this one. Little g delta. There's a plus here and there's a plus here. I mean, the minus became a plus because I changed variables. I changed variables to theta 1 minus z, so the measure picked up a minus, so this minus turned into a plus, and that plus, well, now it's pointing to the left, so it becomes a minus. But what is left now are these two pieces of the big contours which are stretched over here. So these look like integral from minus limit to 0 of dz. So the first one is it's already clear for these two to combine correctly. We need to impose that bz is equal to is symmetric. So let me use that. Okay, so as we go on top of the branch cut, we get some factor of e to the minus I pi minus 2 pi I delta pi from this term. And then we get a factor of e to the I pi delta from this term, according to the equation. And the function that we get is minus z times the block and z over z minus 1. And so I'm just using that relation. That's coming from this term, and what I get from this term is the same thing with the opposite phases. 2 pi delta phi minus I pi delta. Okay, so this is already the cosine that we want. So this produces cosine, and this produces the 1. Well, you can probably do the steps more carefully on your own.
So Talking behavior of B at large Z allows you to drop the arc.
Yes, the import. It's actually much stronger. That's not behavior is way stronger than you need for this, but in particular, it's enough for dropping the arcs to infinity. So what have we arrived at now? We have the first term. Now let's make sure this term is not there because it's not wanted. It's some stupid integral from 0 to 1/2. So we'll set this to 0. And this is actually 2 because we already imposed b is equal to b minus z. So these are the equations that we want A and B to satisfy. And under those, if those equations are true, what we have derived is this. So the first term is on the board, the second term is 0 because of the equation, and the third term is we need to change variables from z to z over z minus 1. So you get 2 cos of pi delta minus 2 delta phi, integral from 0 to 1. So there is a dz missing here. If you change variables from z equals to z over z minus 1, you find the following thing. Find 1 minus z to the power 2 delta phi minus 2 times b at 1 over 1 minus z times little g. Okay, so finally, to be able to combine these two terms together, you need a to be the same as minus this. So the final constraint is that a of z is minus 1 minus z to the 2 delta phi minus 2 times b over 1 minus z. And if that is true, then you arrive at 2 cos squared pi over 2 delta minus 2 delta phi integral from 0 to 1 and z g delta z, which is what we need for the proof to be true. So what do we have? We have two functions a and b which satisfy those two equations in the box and this equation. So let's just express a single function equation for b. So let's just substitute from here into here. If you do that, you get the final equation for b, which is that b of z equals 1 minus z to the 2 delta phi minus 2 b 1 over 1 minus z plus z to the 2 delta phi minus 2 b at 1 over z. And remember that b is symmetric. Then once we find a b, then we can find an a from here. So if we can find a b such this is satisfied, then we solve the problem. We still need to check that a is positive, right? For positive. But this will be true for the unique solution. Let me just quickly do that. So let's write some ansatz for B. Well, the simplest ansatz that decays. So remember that B needs to decay at least like a -1 minus epsilon, but it's symmetric. So the natural points for this problem are 0, 1, and infinity. B is symmetric. So the simplest function that you can write down is this one, right?
1 second, because the died. Okay.
This is the simplest function that you can write down that satisfies the right decay and that has natural poles. Delta phi minus 2 B ansatz. So the only points where something can happen here are 0, 1, and infinity. This function is symmetric under z goes to 1 minus z. It needs to decay at least like 1 over z. So the simplest function that you can write down is this one. Well, let's see if it works. Whether it works depends on delta phi. So you see that for something like this to have a chance to work, delta phi should be half integer integer. Oh. No, I think
There's 2 plus.
yeah, it's 2 pluses. Well, it's a minus. I just put them on the same side. Like that. If it's the left-hand side, it's minus right-hand side. Okay, that doesn't work. Let's see if it works for some other values. Okay, still doesn't work. Okay, so what can we do next? The next thing is to increase the order of the pole.
Okay.
Increase the order of the pole, and then we can afford to put in something upstairs, which is like this. Now this is a kind of degree 1 polynomial in the symmetric variables e1 minus e. The degree 2 polynomial, so this still decays sufficiently fast, but gives us some more leverage. Let's see if it works for delta phi equal to 1. It doesn't look like. Okay, can we find A? Aha! Then A is equal to minus 5 halves. It worked. Oh, what did I do? 2 over plus 5. Sorry, 2 minus 2 over 5. Okay, so we solved the problem for delta phi equal to 1/2. So this B shows that the generalized fermion with free fermion of dimension 1/2 saturates the optimal upper bound. For 3/2, we can also do it actually. So when it turns out that for 3/2 you can use a equal to minus 2 over 7, and it works. Unfortunately, this simple ansatz doesn't work for any other values of delta phi, which is what makes these two values special. And these two values present them up to the 8 and 10. But actually, with Miguel, we found B, which works for any delta phi, but it's much more ugly. It's some hypergeometric function. For any positive value delta phi, there is a solution of the equation, but it's not a rational function anymore. It has some cuts. You need to be a bit more careful with the contour manipulations to avoid the cuts and so on. But there's a solution. Basically, it is. So if you want to solve it with rational functions a and b, then 1/2 and 3/2 are the only places where it works. Which is why Vyazovska could solve the sphere between 8 and 24 dimensions only with modular forms. Under this mapping, the rational function would become modular forms. It's much simpler in the CFT language where you just do rational functions. You don't need to know anything about modular forms.
What happens if you have functions with branch cuts? What do they turn in the sphere packing case? Inside of modular forms?
Well, there are some logarithms of modular forms, basically. Yeah, I think I'm already a bit over time, but okay. So what I explained is that for 1/2 and 3/2, I mean, maybe you should also check positivity, but you can, okay. The exercise is to check that A has the right sign in 0.1, once you apply that, that's true.
But your rational instances.
Yeah. In fact, so for any half integer delta phi, you can do it if you add something like a log, something like this, I think.
Rational instances 1 over c1 plus a divided by 0 minus g squared equal plus b divided by weight second. It's equivalent d divided d 1 minus c cubed.
You would indeed. That's what I tried at first, and it didn't work. So it turns out that you need to log for all other values of delta phi. Okay, well that's it for today. Unless there are, I hope there are.
You find an answer for omega looking at the box equation in the top blackboard. Omega is a rational function in delta, right?
No. The omega is an integral. Right? A is a rational function, but G is something complicated. You can actually do this integral in terms of the digamma function or delta phi equal to 1/2. Not obvious that you can, but for the special values of delta phi 1/2 and 3/2, there is a closed formula for this integral. You need to integrate some rational function times hypergeometric and be done.
It's only on the real line that it's real analytic, right? Because it needs to have this shape that you described.
It has some poles on the negative real axis.
So it's a rational function as a function of delta.
No, it's not rational at all as a function of delta. A is rational of z. Then you do the integral and you get some digamma function, which is not rational at all.
But then, in the plot that you showed with the zeros,
it has infinite limit of zeros. It can be rational. It's basically cos squared times something positive.
I think omega, for this step, you said you impose that omega and omega prime and those threshold operations should vanish. Is that actually used to find in?
Yeah, I mean, what we use that we can put this cos squared outside. That guarantees it, and because it's now a finite integral. I mean, it's finite when delta is above 2 delta phi plus 1. It's infinite when delta is less than 2 delta phi plus 1. That's why that's how the double zero becomes a simple zero.
More questions? Okay, so thank you, Dalimil.